Hey there, Jana Matrick Myers, and today we are looking at 2.2 from the ZIL text, Separable Equations. So I'll tell you right now, this one will seem pretty mean. It's got some mean integrals if you haven't quite grasped integration techniques. But just follow along, do the best you can. Hopefully, since this is a means to a higher level skill than just finding an indefinite integral, it'll make more sense this time around. All right, so I'll show all the work, but hang in there. You can do this. You got this. All right, so the simplest of all differential equations are first order equations with separable variables. This does not mean, like I was saying, this section will be easy. We'll walk through several different problems to help refresh your amazing integration skills. Solution by integration. Consider the first order differential equation dy dx equal to some function of x and y. When f does not depend on the variable y, so that is your f of x and y is some function g of x. It's like what you've done before in other calculus classes. The differential equation dy dx can be solved by integration. Dy dx equal to g of x. If g at x is a continuous function, then integrating both sides of dy dx equal to g of x results in y equal to the integral of g at x with respect to x, which is some capital G at x plus c, where capital G at x is an antiderivative of g at x. All right, so definition 2.2.1, separable equation. A first order differential equation of the form dy dx equal to g at x times h at y is said to be separable or to have separable variables. Note, there is no need to use two constants in the integration. Of a separable equation, since a difference of constants is just another constant. We will often be relabeling constants in a manner convenient to a given equation. So for example, let's say you have e to some constant 1. Well, e raised to a constant is just another constant. If you double a constant, that's still a constant. If you add or subtract two constants or more constants, you would get another constant. All right? So sometimes you could lose a solution. So care should be taken when separating variables, since the variable divisors could be 0 at a point. Specifically, if r is a 0 of the function h at y, then substituting y equal to r into dy dx equals g at x times h at y makes both sides 0, which means that y equals r is a constant solution of the differential equation. But after the variables are separated, the left-hand side of dy over h at y equal to g at x dx is undefined at r. Therefore, y equals r might not show up in the family of solutions that are obtained after integration. And simplification. So this type of solution is called a singular solution. All right, so let's take a look at this first example. Please solve the given differential equation by separation of variables. All right, well, the evil plan here is to get dy on one side and dx on the other side, and then we want to see if we can get all of the y's as factors of dy and the x's as factors of dx. So if I add y minus 1 squared dx to both sides, I get dy equals quantity y minus 1 squared dx. Now, dividing both sides by y minus 1, the quantity squared, I'll have dy over y minus 1, the quantity squared, equals to 1 dx. You don't have to write the 1, but that way it won't be like a so easy it's hard thing to integrate. Okay, continuing, let's write this in a form that's more amenable to integration. And now when I integrate both sides, you could do a u substitution on the left side, but the derivative of y minus 1 is just 1. And so I'm going to go ahead and just evaluate that derivative. We'll have the quantity y minus 1 raised to the negative 1 divided by negative 1 using the general power rule for integration, and that's going to equal to x plus some constant c. So that's going to give us negative 1 over y minus 1 equals x plus c. So what we want to do is isolate the y term. So doing some simplification, we would get negative 1 over quantity x plus c equals y minus 1, and then 1 minus 1 over x plus c is equal to y. So y equals 1 minus 1 over x plus c, and we're all good to go. Cool, cool? All right, perfect. Now, here we go. Next example. E to the x times y times dy dx equals e to the negative y. Okay, so let's get that e to the x term away from the dy dx. So we'll have y times dy dx is equal to e to the negative y plus e to the negative 2x minus y all over e to the x. Okay, so next up we will have y dy dx equals e to the negative y minus x, so I'm dividing each of those terms through by e to the x, plus e to the negative 2x minus y minus x, using properties of exponents. So we'll have y times dy dx equals e to the negative y times e to the negative x plus e to the negative 3x, combining these two terms, times e to the negative y. Now, factoring out e to the negative y, we will have e to the negative x plus e to the negative 3x. And then multiplying both sides by e to the y, we'll have y e to the y times dy is equal to, move this down, is equal to the quantity e to the negative x plus e to the negative 3x dx. So I multiplied both sides by dx over here. It divides out on that left side. Perfect. All right. So now we need to integrate both sides now that we've separated the variables. On the left side, what do you think we're going to have to do? Beautiful. Integration by parts, right? So, this is the left-hand side. If we let u equal to y, du equals dy, dv would equal to e to the y dy, and so v, integrating both sides, will be e to the y. So the integral of y e to the y then, with respect to y, will be equal to u times v, so y e to the y minus the integral of v, which was e to the y, du, which is dy. So that would give us y e to the y minus e to the y. All right, so we're going to put that in the left-hand side, y e to the y minus e to the y equals negative e to the negative x, that's the antiderivative of e to the negative x, and then minus 1/3 e to the negative 3x plus some constant. Now this one will end up being an implicit solution, so let's just get everything except for the constant on one side. So we'll have y e to the y minus e to the y plus e to the negative x plus 1/3 e to the negative 3x equals C, and we're all done. Not a horrible integration by parts problem, right? You got this. All right, perfect. Now, let's go ahead and take a look at this one. So, we have dy on the right side, dx on the left side at this moment. So, I'm going to rewrite this as x over, I'll rewrite this as a rational exponent, 1 plus x squared to the 1/2 times dx. That's equal to y over 1 plus y squared to the 1/2 dy. All right, now we're using negative exponents and swapping the terms. So we have the y's on the left. We have y times quantity 1 plus y squared to the negative 1/2 dy is equal to x times 1 plus x squared to the negative 1/2 dx. So here's the thing. when we integrate both sides, the substitution will be the same on both sides. The derivative of the quantity being raised to the negative 1/2 on the left side is 2y. I already have the y. I need a 2 multiply on the outside by 1/2. Similarly, we'll do the same on the right side. So that's going to end up giving us, so this is our derivative, we'll have 1/2 times quantity, 1 plus y squared to the positive 1/2 divided by 1/2 equals 1/2 times 1 plus x squared to the positive 1/2 divided by 1/2. So these 1/2s divide out on each side. And then, we have our plus c over here. So we'll end up at the end of the day with the square root of 1 plus y squared equals the square root of 1 plus x squared plus c. Groovy? Again, it's in implicit form, but that's cool. We're just getting used to isolating or getting the y's with the dy and the x's with the dx. Groovy? All right, so here are some more fun examples, all right? So we have part D. This one, when I see terms like this, 4 terms, I look at factoring by grouping, okay? This is probably a little small to you. So I'm going to say that dy dx equals, I can factor out a y from the xy plus 2y in the numerator, and I'll be left with x plus 2. And then if I factor out a negative 1 from the last 2 terms, I'll be left with an x plus 2 over, this time, again, I can factor out a y. I'll have x minus 3. And then if I say plus 1, I'll still have that x minus 3. So now I'm going to look at factoring out common factors. So in the numerator, I've got common factors of x plus 2, and in the denominator, it's x minus 3. So, when I factor out the x plus 2 in the numerator, I'm left with y minus 1 over factoring out x minus 3, I'm left with y plus 1. And if I multiply by the reciprocal of those 2 y factors, that fraction there, I'll get y plus 1 over y minus 1 dy, getting the dx on the other side. I'll have x plus 2 over x minus 3 dx. Cool? Now, don't go crazy and make up your own canceling rule. It's very tempting here, but remember that if you have the numerator is the same degree as the denominator, or if the numerator has a greater degree than the denominator, then you can use long division. So, working on the left side, y minus 1 is the divisor, and y plus 1 is the dividend. And so y goes into y once, so I'll multiply the 1 through the quantity y minus 1 subtracting the whole term, I will end up with a positive 2 as the remainder. And so this will be plus 2 over the divisor, which was y minus 1. Now, for the x term, we'll have quantity x minus 3 as our divisor. And our dividend is x plus 2. X goes into x once. And we get x minus 3. Subtracting x minus 3, the whole quantity, we'll have a 5 remainder. So this will be plus 5 over x minus 3. Cool, cool? All right, let's rewrite that stuff. So on the right-hand side, I'm going to have I'll do the left-hand side first. On the left-hand side, I'll have 1 plus 2 over y minus 1 dy. All of this will be times dy equals the quantity 1 plus 5 over x minus 3 dx. Integrating both sides, we'll have y plus 2 natural log. I don't need the I'll do absolute value, y minus 1. And that's going to equal to x plus 5 natural log absolute x minus 3 plus, and cleaning it up, we'll have y plus natural log quantity y minus 1 squared. That's equal to x plus natural log absolute x minus 3 to the 5th plus c. Now, let's take a look at what we have. We'll get natural log y minus 1, the quantity squared. So I don't need to put absolute value bars around that one because I'm squaring it, so it'll be positive. And then minus natural log absolute quantity x, oops, sorry, this should be a 3, x minus 3 to the 5th equals x minus y plus c. So I can get the difference of natural logs is the quotient, right? So I'll end up with 1 happy natural log. In the numerator, we'll have y minus 1 squared. In the denominator, we'll have absolute x minus 3 to the 5th. That's all in the natural log. That'll equal to x minus y plus c. Now, a logarithm is an exponent, right? So if I write this in exponential form, then I will have e to the x minus y plus c equals what's inside the log, which was y minus 1, the quantity squared, over absolute x minus 3, and then to the 5th. Now the numerator is always positive, and exponential can't have a negative output, so we can remove those absolute value bars from our work. And then this is going to now be e to the x minus y times e to the c equals y minus 1 squared over x minus 3 to the 5th. And then renaming that constant e to the c, c1, we'll have y minus 1 squared over x minus 3 to the 5th equals c1 e to the x minus y. Groovy? Okay, example 2. Now we want to find an explicit solution of an initial value problem. Okay, so we have dy dx equals y squared times sine at x squared. Okay, so when you separate this one, you have to be a little careful. You'll end up getting dy over y squared is equal to sine at x squared dx. Now, the right side won't be, or the left side won't be an issue. Just have y to the negative 2 dy equals sine at x squared. But the right-hand side, you might have noticed, is a non-elementary function, meaning that we can't integrate it analytically, just like e to the negative x squared. So here we go. We're going to rewrite these both as integrals in terms of t, using t as a dummy variable. So what we'll have is this. We'll have the integral, and I'm looking at my lower limit of integration, right? Or actually not lower limit. I'm looking at negative 2 as our x value from the initial value. So negative 2 to x. And then we're going to have y to the negative 2 at t dt. That's going to equal to the integral from negative 2 to x of sine at t squared dt. So now the left-hand side I'm going to be able to work with, all right? Because it doesn't matter. I'm just going to get y at t to the negative 1. Put this in a quantity so it's not confusing looking. Over negative 1 evaluated from t equals x, or t equals negative 2 to t equals x. And that's going to equal to the integral from negative 2 to x of sine at t squared dt. So, working on this left-hand side, we'll have a negative 1 over y at x minus 1 over y at negative 2, which we already know. That's going to equal to the integral from negative 2 to x of sine at quantity t squared dt. All right, so now working on this, we will have negative 1 over y at x plus 1 over y at negative 2 from our initial value statement was 1/3. So we'll have 1 over 1/3, and I distributed the minus through, and that's going to equal to our definite integral from negative 2 to x of sine at t squared dt. So that will be negative 1 over y at x is going to equal to 1 divided by 1/3 is 3. I'm subtracting 3 from both sides. And I'm keeping this definite integral going on here. And then now when I go ahead and get y at x in the numerator, multiply through by the negative, we'll have y at x is equal to the quantity positive 3 minus the integral negative 2 to x of sine at t squared dt. That whole thing will be raised to the negative 1, part of getting y at x in that numerator. Okay? And that's it. Believe it or not, that is the answer. Interesting, huh? Okay, example 3. Please find an explicit solution of the given initial value problem. Determine the exact interval of definition by analytical methods. So no computer. All right, so we have, let's see what we have. We have terms that have x only on the right side and terms that have y only on the left side. So that's kind of nice. So we'll just multiply both sides by dx. We'll have 2y minus 2 times dy is equal to the quantity 3x squared plus 4x plus 2 times dx. Now, integrating both sides, let's see what happens. We're going to get 2y squared over 2, which is just y squared, minus 2y equals 3x cubed over 3 is x cubed, 4x squared over 2 is plus 2x squared, and then plus 2x plus c. And continuing, let's see what we have. So we want to solve this. So this one, it's like kind of, it's implicit right now, okay? In order to get this explicitly in terms of y, then we need to complete the square. So here, if you add negative 1 squared, which is just adding 1, and we'll be doing that to both sides, then you'll end up with the quantity y minus 1 squared on the left, right, is going to equal to x cubed plus 2x squared plus 2x, and call this one constant 1, because a constant plus 1 is another constant. But now we want to use our initial value condition, right? So we know that y at 1 is negative 2, okay? So I'm going to plug in negative 2 wherever I see a y, and then 1 wherever I see an x, so that I can get a particular solution. So I just plugged in negative 2 wherever there was a y, and I plugged in 1 wherever there was an x. All right, whoops, sorry. Okay, so this will be, and sorry, this whole thing was squared. So we'll get negative 3, the quantity squared, is equal to 1 plus 2 plus 2 plus C1. 9 equals 5 plus C, subtracting both sides of the equation by 5, we'll get 4, and these were C1s, is equal to C1. Now, back substituting it back in, okay? And then we want to also isolate y. So we have y minus 1, the quantity squared, equals x cubed plus 2x squared plus 2x plus 4. If I square root both sides, I'm going to pick the positive, or the negative square root, sorry, because of this negative interval for y. All right? So, y minus 1 is going to be the negative square root of x cubed plus 2x squared plus 2x plus 4. And then getting 1 to the other side, we'll have 1 minus the square root of x cubed plus 2x squared plus 2x plus 4. And we're all done. We've gotten our initial value solution solved with y isolated explicitly in terms of x. Groovy? All right, beautiful. Okay, example 4. Use a technique of integration or a substitution to find an explicit solution of the given differential equation or initial value problem. So in this case, it is an initial value problem, all right? So, this one might be a wee bit tricky. We might need an integration by parts. First, let's separate these variables and get dy and dx on different sides. So we've got y dy equals to, if you don't mind, I like the arc notation better. Arc tangent at x is equivalent to the inverse notation used above. And then we have our dx. Now, this is kind of a classic. On the right-hand side, this is sort of a classic integration by parts problem. And so we'll do it together. Here we go. We're going to let u equal to arc tangent at x. And it's kind of quote-unquote easy because the arc tangent at x doesn't have, an antiderivative that is easy, right? It's not one of your basic antiderivatives. And so it has to be the u. So our du will be dx over 1 plus x squared. dv will be, all that's left is our x dx. And so integrating both sides, we get v is x squared over 2. So now our integral of arc tangent, of x times arc tangent at x with respect to x is going to be u times v. So writing that pretty, we'll have x squared over 2 times arc tangent at x minus the integral of, so we've got a 1/2 on the outside. V will be x squared. The 1/2, the over 2 is taken care of on that 1/2 on the outside. And then times dx over 1 plus x squared. So this will be x squared over 2 arc tan x minus 1/2 times the integral of. So here again, kind of messy, have to do multiple things. We can divide, so our divisor is 1 plus x squared. Actually, let's write it as x squared plus 1. And then that's dividing x squared. I'll just say plus 0x plus 0. And then I'll have one of these. I'll get x squared plus 1. I'm subtracting that. So then I'll get a negative 1 as a remainder. And I'll have minus 1 over, I'll rewrite it as 1 plus x squared to set up the integration. So, bringing it back, and actually I'm going to kind of drag this down the page. I love this feature. And we will have quantity 1 minus 1 over 1 plus x squared dx. So, continuing, whoops, this gives us x squared over 2 times arctangent at x minus 1/2 times x minus, lo and behold, we have 1 over 1 arctan at x over 1, right? So just arctan at x plus c. All right, so putting this in on the right-hand side, we're going to end up with x squared over 2 times arctangent at x minus x over 2, I'm distributing the negative 1/2, plus 1/2 arctan x plus c. And then on the left-hand side, we'll have y squared over 2. Multiplying both sides by 2, we'll get y squared equals x squared times arctangent at x minus x plus arctangent at x plus, let's call it c1. And we're done. Oh, done with the, sorry. Done with the integration. Now let's apply our initial value, okay? So y at 0 is 3. So, n for y, sorry, we'll put 3. So we'll have 3 squared equals 0 squared arctangent at 0 minus 0 plus arctangent at 0 plus c1. So, just showing you what I plugged in where. So this will be 9 equals 0 times 0 minus 0 plus 0 arctangent, the angle at which the tangent function is 0 is 0 from your domain of negative pi over 2 to pi, non-inclusive, and then plus c1. So it turns out that c1 is 9. And then rewriting, we will have y squared is equal to x squared arctangent at x minus x plus arctangent at x plus c1. And then, nope, sorry, plus 9. And then isolating y, square rooting both sides. We're going to choose the positive root because y had a positive value when we applied our initial condition. And so we get the square root of all this. And I'll put it back in the other notation. And we're all done. And that's it for today. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please hit that like button and subscribe. Bye.